Okay, let's come back. Um, um, so I hope you guys are still here, and so we talk about okay, SFE code, and then essentially I just want to give a comment, a remark of like the entropy equation again. It's okay, let me just here. So so I hope that by this time you are very familiar with this equation now. If you have the entropy of a source X is basically like Px times log Px, right? Or like, let me put it like log 1 minus Px sum over all X. And so as we mentioned that like this is basically how far you can compress the source, like into how many bits. And actually if you look at this equation also, like from yes,
should be log 2 or log?
Actually, yeah, this is a very good question. Is log 2? You can assume it's log 2 because it's more common when you use log 2. What is the difference if you use log and log 2? As you can see, is just if you have log 2, for example, if I log base e something, let's see, how do I write it? If I have a log base 10, x is equal to log ln x over ln 10, right? Something like that, right? So when I use different log, it's basically just different by a constant, right? So therefore, like whether you use log 2 and lateral log, what you differ is basically just multiply by a constant. That will corresponds to different units. So when you use log base 2, the unit is bits basically, so it's more lateral, or actually more lateral for people now, you can count it. But at the beginning, people would like to use the lateral log. It's a more lateral unit that they have a unit called lat. So if you use lateral log, it's like, but most of the time I think you can just assume it's log base 2, and because people nowadays are much more familiar with like bits. So and also like what I want to say like just now is, if we think of the optimization, how we get this formula, we go through the optimization to minimize the length, expected length, with the condition of the Crafts inequality, and the outcome is that the expected length, like for simple x, will be like log 1 over px, right? For if the symbol like have a probability px. And this thing is actually pretty lateral if you think of that, because for example, like if I have x is equal to 0.25, so it's just like that. I have actually, you can think of that this x is like it's almost exactly like you have something that have like 4 different outcomes, right? When I have something, okay, or like put it the other way, if you have something have like 4 different outcomes, then each of the outcome will have probability 1 over 4 is equal to 0.25, right? So therefore, like, and when you have 4 outcomes, like how many bits do you need to compress that? That would be just log 2, right? Oh, sorry, log 4 would like equal to 2, right? So therefore, like, and what's 4? 4 is just equal to 1 over 0.25, right? So if you come to think of that way, like everything's become pretty lateral. So anyway, I just want to remark for that, if in case it make this like even easier to remember. And okay, now let's go look at some property of this entropy thing. And let's first just consider a binary case. Like, let's say x just take 2 values. For example, like the example we had earlier, last time, just flipping a coin, it can take head or tail. So then if we draw this hx here, so of course hx here, okay, of course, okay, one thing I want to emphasize also, like it's very common to draw to write the rotation of an entropy of some source as hx for some source x. But of course, like, this entropy function actually depends on the distribution of x instead of x itself, right? So when I draw this is actually some function of like this px, actually is some function of this px instead. And p is the distribution of x. And for example, like in this case, if I only have like 2 possible outcomes, then I only have one parameter p, right? So let's say this is a p is equal to probability of head. So what you expect is that, like, okay, what is p equal to 1/2? What do you expect, like, hx supposed to be?
Maximum.
Yes. And what will be the value?
0.5.
Not exactly. You look at this one.
Oh, here 1.
Yes, it will be 1. Yes, it's 1 because I think of that if you have like only two values, is uniform, then just go back to classical combinatory, to count like how many bits to kind of store this 1 bit this like 2 outcomes will be just 1 bit, right? So therefore I need 1 bit for that. And how about like when p is equal to 0 and 1?
That's 0, 0.
Yes, in that case there will be no information, because when you already, if this is something like deterministic, basically, like it will be always head or always tail, there will be no information. And if you plot the whole thing out, it will be something like this, where you say some concave shape here. So it's like a bowl turning upside down. And this is for like a binary case here, just an example. Okay.
So the entropy is to measure uncertainty there. How many information?
Yes, actually I didn't emphasize that also, yeah. Because you think of that, what was entropy doing is, I think, how much you can compress, right? If you have that source, how much you can compress that. And that will depends on like how much uncertainty of that source also. If the source is completely certain, if deterministic, then there's nothing you need to compress. So it's already known. So on the other hand, if it's like completely uniform, it's like most random in the sense, then you will need more bits to store. Yeah, so in the sense that entropy is a measure of uncertainty. And okay, I will just follow what I'm doing in the slide. I like to introduce, this is like for the discrete case, right? I have the entropy hx is for some discrete source. It's defined by this equation here. Now, if I have some continuous source, like if I have kind of like I have some y here, is continuous. For example, y is like continuous over some values like from 0 to 1, let's say. Then in this sense, I cannot use this definition because I cannot just say what's the probability of kind of, let's say y equal to 0.5, because if I have a distribution, if I continuous variable like this, if I ask like what's the probability of like y is equal to some point, like some particular value, that will be always equal to 0, right? As we mentioned that at the beginning of this course. So therefore, like if we basically we cannot sum over that. So in that case, we need the integral instead. So we have a differential entropy that's defined for, this is a differential. Yeah. So hy will be like some integral. It's exactly the same thing. Let me write like py minus log py dy. But be careful that here, like p here is not the PMF, it's the PDF now, the probability density function, right? So and we can define this thing. And one remark I immediately want to give is if you look at hx here, because px is the probability itself, right? So px is always have a range, like it has to be bigger than equal to 0 and less than equal to 1, right? So therefore log 1 over px, this thing is always bigger than equal to 0. Yeah, so therefore, like, of course, px is bigger than equal to 0. So therefore, hx is always bigger than equal to 0. But it's not the case like for the differential entropy here. So be very careful. Like this can be negative. It's possible. Because if this is py, it's not exactly probability, right? This is just a probability density function, and this is something I want to emphasize. So now just look at a simple example first. Like let's say if I have again a continuous source, I say now with again uniform distributed, but instead of over 0 to 1, let's say from 0 to a. So then if this is a uniform distributed, okay, by the way, what is this level here? This is a okay, if this is a py here, what's this value here?
That is uniform.
Yes.
PDF.
Yes.
Should be 1 over a.
Yes. It will be 1 over a because the total area should be
1.
sum to 1. Yes. Now then let's compute that. Like what's hy? In this case, hy is my py, not py again, dy. I have a minus sign here. So py, so basically I should take integral from 0 to a minus, so py is all 1 over a, and this is a log 1 over a. So or log minus log 1 over a is just log a here. So and this dy, actually this is just equal to log a. Right, because this is dy, so from 0 to a is just a, right? A and cancel, and this is just 0 log a. Yeah. Now, so as you can see now, like when a equal to 1, then this hy is equal to 0, right? But when a is less than 1, then I will have like hy is negative, as I mentioned earlier.
Yeah.
The h can be negative. The differential entropy can be negative. Yeah. Let's do one more example. Like let's do let's t is kind of like exponentially distributed. So the exponential distribution will have yes.
This is not ui because this is here. This right?
Oh, this is one. But this is a py, right?
Yeah, that's py. That's
Py
py.
is equal to 1 over a, right?
Yeah, that's right.
In the range like 0 to a, like py is just 1 over a, and so it's therefore is yeah.
So that means that we don't have any integral from this one is something like constant and dy is y.
Yeah, this is a constant. I can pull it out. So dy,
It's y.
so it's just a, because I integrate over from 0 to a, right?
Yeah, it's only a.
So that got cancelled, like
Oh,
1 over
yeah.
a and 1 over a can cancel.
Oh yeah, okay.
So
That's
yeah.
right.
Now go back to this example, like for exponential distribution. So I think like okay. Hopefully I write correctly. The exponential distribution, I think the PDF is something like that. Yeah. I'm not 100% sure. Let's see. Oh, wait a sec. This.
That's something like a gaussian PDF.
Oh no! Actually, the PDF is something like that, like from 0 to infinity, and then it's like decaying. So let's see if I do an integral. It looks like it's correct. Something like and the mean will be something like let's see.
Maybe in the front
Yeah.
of exponential is constant, not lambda anymore here. It should be constant, a or b, because lambda times 1, so it will be always not going to this one. Because it's bigger and this is smaller.
Oh no, there's a t here. So this is t. This is pt here.
Oh, that's t. Oh,
Yeah, there's a t here. So this is a t decaying here.
oh okay. That's right.
Why small t here? Yes. And actually, you can verify that like the mean of this distribution is just equal to lambda. Basically, that is if I compute the expectation of t, something like lambda t exponential minus lambda t dt. If I do the integral, supposingly I should get lambda.
Yeah, okay.
Supposingly. So then let's see. So if I want to compute the differential entropy for this distribution here is equal to integral pt log pt. Oh, actually, that's the thing is I want to show is the integral we will. Okay, when we write it this way, it's actually, if you look at that, it's actually also is really just the expectation of minus log py, right? Is that reasonable? Right? You think of y is a random variable. Now py is a function of y, right? So therefore it's a random variable. So and log py again is a function of y is a random variable. So you can look at the expectation of that, and this. If you write out the expectation of this guy is just equal to this, right? Yeah. Or something like for anything, if you have like expectation of fx will be just equal to if it's continuous, it's just equal to px fx dx here. So here just like f is equal to minus of p. Now so that's if you know the I want to show that because when you know the mean, sometimes you don't actually need to go through the integral or something, because this is actually the differential entropy, therefore it's just equal to minus log pt, right? And pt is equal to this guy here, so therefore it's equal to minus log the first guy, log minus log lambda, and then plus I have minus and plus lambda t, right? Yeah. Log lambda, of course, this is just a constant. I can pull it out, so it's just is equal to minus log lambda, and then oops, actually, okay, this is not correct. So the expectation of t should be equal to 1 over lambda if you try to compute that. Okay. So then or if you can just check it on Wikipedia, it should be equal to 1 over lambda. So and for this guy, so therefore like expectation of lambda t is just equal to lambda expectation of t, right?
Yeah.
So just equal to plus lambda expectation of t is equal to 1 over lambda, so that can cancel, it's just 1. So therefore it's just 1 minus log lambda. That's the for exponential distribution. Okay, I'll go for a couple more. I think this is, let's see, I can move around too far away. So this one will be more useful is the Gaussian case. Like we first consider a univariate Gaussian or univariate normal. So
we could calculate for every PDF the entropy of them. So that is the
yes, or actually you can look up table, but I'll go for some of them. For example, like for the Gaussian case, because it's kind of pretty and actually it's actually afterward I probably will spend some time talk quite a lot of Gaussian, because it's of course you have the central limit theorem to argue that many eventually you have lots of independent things mixed together, you get something Gaussian. But at the same time it's kind of the distribution, only distribution is very tractable, so therefore we spend some time on that. So just a review for that, if I have Gaussian x is let me write it this way, have a mean mu and variance sigma square. I call univariate is a scalar Gaussian, just one random variable here. We will talk about joint Gaussian afterward. So the PDF, or maybe I also write down PDF. The PDF is more complicated. It's something like 2 pi sigma square. This constant usually we don't need to worry too much about that most of the time. So and this is x minus x minus mu square over 2 sigma square, something like that. That's the Gaussian PDF. Now again, if I try to find the entropy of x, then I'm going to compute this way, expectation log px. So actually I better write better. This is a big x to be right. I should be careful with notation. When you do expectation, it's always expecting a random variable, right? So therefore this should be like a big X instead of a small x. So this just put into that, then I have like expectation minus log. I have or like plus log 2 pi sigma square, and then minus, and minus will be plus again, like plus x minus mu square 2 sigma square. Here I using lateral logs, just makes things simple. So here I'm assuming this is so therefore what I compute will have a unit net. So otherwise I have some log 2 coming up, it's kind of ugly. So
it means that sometimes we can use
log
2, sometimes we can.
It's just for convenience, because the only difference would be like there's a kind of constant changes, and then anyway it's just a different unit, right?
Yeah,
so
different unit. All the outcomes.
So here I just use lateral log, will be easier. Actually not. The slide I didn't use lateral log. Don't use lateral log then. Actually I use the log 2 here. Probably like I want to have a unit of bits. So if I don't use lateral log, then anyway, if I use bits here, then I will just have a log base e here coming up anyway, right? Log 2.
So if we use natural log, so what the units called?
We call net.
Oh, net.
Yes. So let's use like this is log 2 here. Then I will have like this is will be in terms of bits anyway.
Yeah.
So I have will be like this. I won't draw this log base 2 anyway anymore. I just assume it's a log base 2. So this is a 2 pi sigma square. This is just a constant. Expectation constant just itself. Now if you look at this case here, this is pretty nice. Expectation of this guy, what is this? Okay, a bunch of that is just constant. I can just put it out. Right? So it's not 2 base e over 2 sigma square expectation x minus mu square.
It should be variance.
Yes, that is just the variance. So therefore, like this is actually just
sigma.
This is just sigma square. Yeah.
Sigma square.
So actually, this just got cancelled. It's very nicely. It just got cancelled. So therefore, like we just have log. And this is actually just 1/2 way. 1/2 log 2 pi sigma square plus 1/2 log e, and then of course this can merge together. Is 1/2 log 2 pi sigma square e, something like that. And this is the entropy for univariate Gaussian. So from this is log 2. Yeah, this is bit. But I would just like assuming it's log 2 now. I'm not going to write log base 2. Yeah. This is log base 2. Yes. Let's consider the multivariate Gaussian. So I have multivariate. Maybe do I have enough? I have enough space. Multivariate Gaussian or normal. So in that case, this will be a vector, right? So this is a vector variable, and it have a mean mu again. Like this mu will be a vector as well, and then you have a covariance matrix like sigma. This is a matrix. Let's say if x is n by 1, then this covariance should be n by n. So the covariance matrix is basically something like that. Right? If you have this x is actually x1, x2 up to xn here, then this matrix is basically the sigma ij element is just equal to the expectation x I minus mu I times xj minus mu j. taking expectation.
So the variance is a metric.
This is called the covariance matrix.
Covariance is metric. And
Matrix. Covariance matrix.
And what type of the mean? The mean is also metric or?
No, the mean is just a vector here.
This vector.
N by 1 vector.
Oh, okay.
So the mean will be like mu1, mu2 up to mu n here. Yes.
Oh, why the covariance is covariance should be metric? How we could describe by using graph maybe?
Figure?
Graphics or signals. Signals.
You mean signals?
Yeah, signals.
Signal?
Yeah, I mean that why the covariance become metric at there.
Oh yeah, because you have you have let's say here you have n of the variables here, right? And the covariance actually describe like for each pair of the variables how they are correlated. So you need to consider each of the pairs, so therefore it will be n squared. You pick the first one, and then so basically this sigma ij, as I say, the ij element will be like this. So if I write the sigma is like pretty big, it will be like maybe I can pull the expectation outside. Expectation outside, this is like x1 minus mu1. The diagonal term will be just the square, x1 minus mu1, x2. But therefore the diagonal term is actually just the variance for each of the element. And the cross diagonal term will be like x1 minus mu1, x2 minus mu2, and so on. And this x1 minus mu1, x3 minus mu3, something like that. And then it will be a matrix. And this is a symmetric matrix, right? This will be kind of. Yes. Yes. And the PDF for the multivariate Gaussian, I think like, yeah, I remember like I took one class from my PhD advisor, like the first class in my master. I guess it's like some image processing, and he asked us what's the PDF for this multivariate Gaussian. He said like, I'll be impressed if you know that, or like you remember that. So it's not that ugly. I don't know whether any of you can. Actually, the exponent is not too difficult to memorize, but the constant factor may be a little bit. Sometimes I don't remember it. So the constant factor is kind of similar to the 1D case, but you have something like that. Okay. I think it should be white like this. Determinant 2 pi sigma and 1/2 x minus mu transpose sigma inverse x minus mu. So and of course the univariate Gaussian is just a special case, right? So you expect that if x is a scalar, then it will just fall back to the Gaussian PDF you're familiar with. So in the case when x is just a scalar, then sigma is just one element, right? It's 1 by 1 matrix. It's just equal to variance is sigma square, right? 2 pi sigma square, and take the determinant is just itself, it's 1 over 2 pi sigma square. And this sigma also like this big sigma will be just equal to like sigma square, and inverse of that is 1 over sigma square. And then this is like, again, it's just x minus mu, x minus mu. So it's like, okay, you can fall back to the 1D case, but this is the basically a high dimensional kind of like multivariate Gaussian PDF. Yeah. And again, we can compute the differential entropy for that. Like for hx here,
Estimate.
this is equal to minus log px again, right? And then this is equal to expectation minus log, or like I can write log determinant 2 pi sigma. The minus side got cancel, and again minus side got cancel. I have exponential. I have like one half x minus mu transpose sigma inverse sigma mu. I'll just skip this bar for the x. It's long to be vector, and I have a log e again, something like that. Now, so again, this is just a constant. I can pull it out like last time. So this part is more tricky. So what we have here is something like, if I look at this here, this is a kind of a row vector, right? X minus mu transpose is a row vector, and sigma inverse is a kind of a n by n matrix, and then I have a column vector x minus mu here. So this multiple, of course, I should get a constant. I mean, like a scalar value here. That's I expect because h is a scalar, right? Yeah.
We can pull out the sigma on there. This one and this one to the outside. So only this one and this one. That's right.
Which one? Log e.
Sigma. This one.
No, unfortunately, you cannot because it's a matrix in the middle, right? You cannot really pull it out. So you can pull out log e. So let's ignore this the first term here. Let's just focus in the second term. So I can pull out log e over 2, but I still have this expectation over this guy x minus mu transpose x inverse x minus mu, something like that. Now, but what we are going to do is we think of like this is basically just a matrix multiplication, right? So let's this multiply by this guy here, or actually think of like this multiplied by this. After this multiplied by this, this will be a vector, right? So therefore, this term here is actually equal to x minus mu I times sigma inverse x minus mu I, right? Right, this is a vector, this is a vector, this multiply that, this is a vector. So it's like the ith element of this multiplied by the ith element of this one here. Now let's continue to expand this guy. What is this thing here? The ith element of this matrix multiplied by this one. So will be something like, so up, this multiplied by this will be like a column vector, right? And if I look at the ith element here, the ith element will be basically this row multiplied by this column here, right? Yes. So therefore should be like sigma inverse the ith row multiplied by this, so it will be like x minus mu j sum over j, right? Is this term here. So I can pull this sum over j outside. So what I have is actually sum over ij x minus mu I multiplied by this x minus mu j. Now everything is scalar now. Actually I can move things around because I can, this is all scalar. I can become like x minus mu I times x minus mu j, right? I can move things around. And remember, I have an expectation outside also. Now because it's kind of scalar, I can actually, okay, let's, my expectation can just apply on this way, and multiply by this is a scalar, it's just the ij term, right? Okay, now the nice thing comes that basically we just mentioned that this is just equal to that, right? So it's exactly identical to this guy here. So therefore, this actually got cancelled, right? This got cancelled out here. This is because this is equal to sigma ij, and this is inverse of this sigma ij, right?
There is sigma ij.
Wait a sec. Oh, wait a sec. Say that again.
This is sigma ij. This one.
Yeah, this one is sigma ij. It's from above. It's here. The ij element of the sigma is just equal to this guy, right? Oh, of course, the ith element of x minus mu is just xi minus mu I, right?
Yeah, that's right.
Yeah, times xj minus mu j, and take the expectation of this, and this thing is identical to this guy here.
Oh,
It's just equal to sigma ij.
that's right.
So okay, anyway, this is sigma ij, so therefore I really have is something like sum over ij sigma ij times sigma inverse the ij element. Okay, what is that?
It's one. No.
Let's see. You have oh, okay. Oh, first of all, I can move things around further. This sigma ij I can put it here is better. Let me move it to here. Sigma ij here. And also, like, because sigma is symmetric, right? Sigma ij is just equal to sigma ji.
Yes.
Yeah, okay. So now I can split this summation again, like sum over sigma j first, then sum over I. So if I sum over j, then okay, it becomes more clear. This is actually it's made the what I have is actually the ith element of a times a, right? If I have of let's call it sigma I is a, let's say this is b here. So remember, like if I have AB, the mn element is actually equal to sum over A, M, J, B, J, and sum over J, right? So if you compare this guy here, what I have here is actually sigma inverse times sigma the ith element, right? And of course, sigma inverse times sigma is just equal to identity. The ith element is just equal to 1, right? So therefore, like this guy here is just equal to 1. Then my sum over I sum n times, so this whole sum eventually is just equal to n.
Equal to n.
Yeah.
Because I is n.
Because I is summing from 1 to n. Yes.
Oh, okay.
Yes. So that's this thing is 1. Then I sum n times I is just equal to n. So okay, finally, we have this thing from the beginning is just equal to n. So therefore, like I have this is expectation log determinant, or like I don't need to expectation. Yes.
Determinant is scalar, therefore we don't need to.
Yes.
Yeah.
We can pull it out actually.
Yeah.
The whole thing is constant.
Yeah, constant.
Determinant 2 pi sigma plus n log e over 2, or something like I can write it as a log e to the n 2 pi sigma. Yeah, something like that.
Where is determinant?
Oh, sorry, I forgot. Determinant, yes. Determinant 2 pi sigma, yes. That's it. That's the entropy for multivariate normal distribution. Oh, actually, I can even go one step further. If I put this E into this determinant, I mean, if you have a matrix, A, if you compute the determinant of NA, the determinant of NA is basically, maybe I call it KA. Maybe I write like that. If I have determinant of KA, where K is a matrix, if A is an n by n matrix, it's actually just equal to K to n A, determinant A.
So it means that if we put n as 1, we can get the equal to the above when the n is 1.
Yeah, it's supposed to match.
Could we?
Yeah, it's supposed to. Yeah, we could check. But wait a sec. Let's do one more step, because of that, I can write it as even a lot more simple form. So I can pull the E inside, and I will have 2 pi E sigma. So it's a count more neat. So this will be the final one.
Yeah.
So now if I consider 1D, then sigma, big sigma is just sigma square, right? So therefore, like my for univariate case, it's just log determinant constant is just itself. So square root of 2 pi E sigma square. So it should be the same as previous case. This one, yeah.
That's right.
Yeah. So that's. Okay, so let me open a new page here. Do I still take pen? Yeah. So we mentioned the difference of like differential and entropy and the original entropy, right? So if I have a continuous source, as we mentioned earlier, we cannot compute differential entropy because we just take the continuous source. We cannot compute the original entropy because if you take the continuous source, it's supposed to have infinite precision, right? Think of like what is entropy mean? Entropy means that like how many bits are required to store this piece of information, right? So if we have a number with infinite precision, we will need the infinite number of bits to store that, right? So now, but we can still hook up like differential entropy and entropy a little, with some relation. For example, like if I have x is a continuous random variable, now we can talk about the differential entropy x here. So now if I kind of like discretize or quantize the x into a quantized version, I call it x delta here. What it means is like delta is the quantization step size. For example, if delta is equal to 0.1, then I will say like for my x is like 0.9213, I'll just quantize that into like 0.9, let's say. So now after the quantization, then x will be like a discrete values, right? So now we can actually talk about the original entropy, and then we can talk about hx delta, right? So what we want to see, like how hx is related to hx delta here, small hx and hx delta, and hx delta is basically, I can write it as the original entropy formula, something like that, right? Log p x delta, something like. Now
so in there, what is an x delta?
x delta is I have the original source, continuous source, then I kind of quantize that. Quantize means that like I will just
Like sail of it or floor.
yes kind of like okay, let me draw a picture. Like for example, my quantization step size is 0.1. What I can do is say from, for example, like from minus 0.05 to 0.05, I all say is equal to 1, let's say. And then from 0.05 to 0.15, I'll all take these values as, oh sorry, I say like this all is equal to 0, I want to say.
Yes.
And this is a basic x delta. So within this range, x delta is 0. Within this range, x delta is equal to 1. And similarly, from 0.15 to 0.25, x delta will be equal to 2, let's say.
What is same x delta is a number. It's not what the value of that. Only 1, 0, 1, 2, 3. So
yes, but you can fill them a number or like a label, right? So as long as you just do a one-to-one mapping, like for whatever x taking like values like within this range, then x delta will be will have the corresponding
corresponding to that.
So then, as we mentioned, like with this x delta, we can compute the entropy. And I guess I need to be careful with symbol here. So this p here is like the probability distribution, or the PMF of x delta here. But we can translate the PMF of x delta with connect the PMF of x delta with the PDF of x, right? So basically x delta should be approximately equal to px x delta times delta, right? The PDF, the PDF, basically the PDF at x delta, then with the width for delta. So if I have that's the PDF of x here, right? So if I quantize, say, okay, this part is, it all go to x delta, then basically the area here is approximately x delta, this height here, multiplied by this, the width here, delta, the height, I mean px delta here, multiplied by width delta, So, okay, then I can substitute this back into this here, so I have sum over minus px x delta log p x delta. So, and then this I can speed it up here. I can px x delta log something like, and I have some log delta here. and I have this P 6 delta delta, something like that. And oh, actually, oh, by the way, here I don't really need to split this px delta here. I can keep this guy. I mean, I only kind of substitute this guy into this one here. For this one, I can just keep the original term here. So I have this here. Now, if I look at this here,
you should put x delta down there. You should put x delta here. Just mean that here.
Oh yes, you're right. Yes, I should put the x delta here, and it's okay. Actually, afterward I may still need that, but anyway, let's see here. Then for the second term here, this is just sum over all the probability, right? For the second term, it's just a constant. So anyway, I will have a minus log delta coming up at the second term here. And for the first term, oh, okay, actually I still should substitute that back. It's a minus p x delta. So if I substitute this back here, I have delta log p x delta. But of course, this is an approximation of integral. Right? If your delta is small, delta go to 0, it's like something like px x delta log px x delta dx. This is just approximation of this way. And of course, this is just the differential entropy of hx. Yeah. So now, therefore, like we see, like we can hook that up. Is after the quantization, hx delta is just equal to hx minus log delta. So it's very reasonable. Like if your delta is kind of small, then you will need more bit to store the x delta, right? Yeah.
When we times this one to this one, this is not only log delta, but should be sigma px delta
Yes.
there. So
Yes, but for this guy here, actually, this one is the probability for x delta, right? This one is sum up to 1. So therefore, like I don't want to substitute first, because this is actually the probability. Let me write better. Let me erase this. Yes, this one is just a PMF of x delta, right? And they should just add up to 1. Yeah, yes. So therefore, like this is just a constant. This should add up to 1. So therefore, it's just equal to this.
So for that on become 1, but
For this
one is not because
for this.
you want to.
Yeah, for this one, because I did, okay, by the way, this is sum over x delta, right?
Yeah.
It's sum over x delta. For this guy, like, I have this one is dependent on x delta, right? I cannot pull it out. Yeah, only this one I can pull it out, and this sum up to 1. Yeah. So actually, yeah, the end result is pretty neat. It's very simple, so you can hook up like hx and the kind of like.
So the entropy is always less than original, the PDF.
No. You mean the entropy is always less than the differential entropy?
Yeah.
No, it depends, right? Because your delta can be bigger than or smaller than 1, right? And be careful, like also this is really an approximation. When delta is small, it's only accurate when delta is small. So therefore, if your delta is pretty big, then it may not be a very good approximation.
Mm-hmm.
But if your delta is small, then it's a reasonable approximation. Yeah. So therefore, like, okay, and when your delta is small, then of course this value will be positive, right?
Yeah.
So it's actually, you will be adding number of bits here.
Mm.
So the smaller the delta, you will need more bits to store. So it's all very obvious. So, but just look at one example, like, of using this, right? So let's say I have some packets coming in following some coming in. Okay, or like some packet. Okay. Okay, I use packet here anyway. I don't know. It's like because I originally I teach this course to some communication students. So, and let's say I need some time to process this packet. Let's say the process time is follows a kind of exponential distribution as we described earlier. So, let's say the average is with an average of 1 millisecond. It means that the exponential distribution with mean 1 millisecond. So remember the mean is 1 over lambda. So therefore, like, lambda, this is 1 millisecond, or is equal to okay, it's equal to 1 millisecond. Let's just use the unit millisecond. So therefore lambda is just equal 1 over 1 minute this millisecond inverse, something like or just
The
one.
means.
That's the
The average.
yes, that's the average, but the parameter is related to the average, to the mean. So actually the parameter lambda is just equal to the inverse of the average. Yeah. So and then okay, so we want to store this processing time. So let's say it's just for a record, like we want to store like this processing time into a table or like into a file. So we have many of this processing time. We want to see like on average, right, how many bits do we need to store this processing time, let's say. And of course it depends on the precision, how much up to what precision we are going to store it, right? If we want to have more finer precision, then we need more bits for storage. So let's say the precision is like 0.01 millisecond. So now the question is like how many bits is needed, or I should say like on average, how many bits needed per record, let's say.
We should calculate first the entropy.
Yes, compute the differential entropy, and then compute. Okay, I think like we already have the differential entropy earlier, right? The differential entropy HT is simply equal to, okay, if this random variable called T, HT is just equal to 1 minus log lambda, right? So, and lambda is equal to 1, therefore it's just equal to 1 here. And if we want to store the precision is 0.01, then basically the final number of bits, like ht delta, would be something like ht minus log 0.01. Yeah, that would be approximately 7.64 bits, something like that. Yeah. So that's one example used for that.
So it means that the packet to be processed need that bit
To store that.
To store.
Yes. If we want to store that, like we will need that many bits, like on average, to store that. Yeah. So let's see. I think I probably should stop here. My next slide is something I already talked about. Is we already mentioned that, like, remember that hx should be bigger than equal to 0. You can just look at the equation. It's obvious because it's equal to expectation minus log px. And px, when it's discrete case, px is always less than equal to 1. So therefore, like, log px minus log px is always bigger than 0. So therefore, like, the average is always bigger than 0. But again, like, small hx can be less than 0. So it can be bigger than 0, but also can be less than 0. And I'm going to talk about Jensen inequality. I'm not sure it's pronounced Jensen inequality or Jensen inequality, but let me do it next time, I guess. Yeah. So I